All right, so let's continue our discussion about efficient transformers. So transformers are getting super popular these days, no matter if it is NLP tasks or even vision tasks. So today, let's first cover what is the basics of transformers, building blocks. So we have previously learned about the CNN architectures, convolution neural nets, MLPs. Right? Now we are going to learn this new species, which is the transformer. Right? And then we are going to introduce those efficient transformer techniques, how to make the computations less, make a smaller amount of computation. And finally, we'll talk about system support for efficient transformers. Let's start with the basics of transformers. Let's see where can it be applied, right? So the first one is, of course, machine translation, translating between different languages, and also a chatbot for question answering. Hey, what can I help you find today? I'm looking for black bike. You posted on IG just now, and then it's going to give you some automatic recommendation. And so chatbot is getting really popular. The most exciting for us is actually the code pilot, right? So GitHub from Microsoft recently get this new feature. You just put some comments, and then Copilot is going to generate you the full code. Very exciting, right? So some of us even tried our homework using Copilot, since we already give you the lot of comments, right? And to let you fill in those information, and it works perfect well to solve our homeworks, right? Although that's not the intention for this class, but I just want to show how exciting this area is. You know, we are all grad students and senior students. We're not just taking the class for taking the class, but we want to learn the stuff. So I recommend not to use Copilot to finish the courses. All right. So given those exciting applications, let's see fundamentally how do we represent the language, the words, right? In order to use deep neural nets to process those natural language, we need to encode, to embed those words into vectors, right? So since we have to do everything in the tensor representation. A naive implementation is, of course, one hot encoding. Like if you have a 10K vocabularies in your dictionary, then we just have one hot encoding for different words. Like the might be 1000, good might be 001. This is good. This is probably a movie, right? Imagine using such encoding. You can have a pretty big vocabulary. Each word will be represented by a pretty high dimension vector with the dimension the same as your vocabulary size, right? So that can be very large. If you have 10K words in your vocabulary, each word should be represented by a 10K dimension one hot encoding, which is super inefficient. Then a better encoding is actually using a high dimensional continuous word embedding, okay? Not one hot through a lookup table. For example, we use 0.2, 0.4, 0.1 to represent the, right? So this is a 3-dimension encoding, embedding, okay, for different words. And the interesting part is that we can do math operations on such words. For example, man minus women will be closer to king minus queen, right? So that's the merit of such word embedding. And we can also train such word embedding end to end with the downstream task. Okay, there are several popular pre-trained word embeddings like word to back below. Those are some pioneer work in this area. So before the transformer appears, when I was doing my PhD, we were using recurrent neural nets and LSTMs to recognize these tags. Right. So let's see how does a recurrent neural net work first. So a recurrent neural net has an input layer, hidden layer, and output layer. Right. These are just MLPs, nothing special. But we have to unroll that across the time dimension. Right? Since we may have different words, different inputs. Okay. So we have one input, the first token, first word, and then we pass it through the initial state. We generate a new state. Well, we can also generate a new output. So given the second state, we take in the second input, combine them together. Okay, every time we're combining the new input with the previous memory state. Okay, and we pass it through an activation function to get an output, which is optional. And we can also get the next state, okay? The next working memory. Okay, so on and so on. We can repeat this process to take multiple tokens, also generate multiple tokens, and finally have a final embedding for the whole sentence. Okay, and there are multiple versions. How do we do this activation function concatenation to take this input and previous hidden state to generate a new output and the next hidden state, either using RNNs or LCMs or GRUs. There are many different versions, but the big picture is the same like this. Okay. Pre-transformer era, people can also use this 1D convolution to model this, languages, right? Since language is basically a 1D sequence. Okay. For example, we can use a window size of 3 to do convolution along this word dimension, right? So each time you can get a receptive field of 3 words, but you can stack multiple such layers so that you can increase your receptive field to be able to see the entire sentence, right? So the advantage is that there's no dependency between the tokens, right? Which is better, leading to better scalability. And also convolution is very well implemented on GPUs and other hardware accelerators. Well, the limitation is that you have a limited window size in a given layer, right? Therefore, it's harder to model those long sequences, long context information, unless you have a pretty deep layer and a pretty large receptive field. So then I debuted this transformer. Okay, so the transformer block contains of 2 parts. Okay, one is the encoder, okay, and the other is the decoder part, right? So for the encoder part, and it again has 2 components. The first is called a multi-head self-attention. Okay, the second is a fully connected FFN feed-forward network. Okay, so we are going to introduce what is this multi-head attention very shortly. But feed-forward network is very simple. It's just 2 layers of fully connected layers, right? And for the decoder block, apart from this multi-head self-attention and this FFN layer, it also has another multi-head attention on the output of the encoder stack, right? Feeding the output of the encoder to the multi-head attention, right? And let's go through each component, like what is positional encoding, what is the layer norm, one by one. And on the big picture, we have a bypass layer. Okay, each time we have a sublayer, we have a bypass. Okay, and we pass it through the layer norm, and then we feed it to the next layer. So let's jump into them one by one. The first one is the multi-head self-attention, short for MHSA. So we have multiple such value. This is key, this is query. Okay? And the basic operation we do here is basically we are multiplying the query with the transpose of the key, okay? Doing the matrix multiplication and scale them, okay? Pass it through a soft, and then we perform this mask, which is optional, okay? And then pass it through the softmax to get the attention map. And finally, we multiply that with the value, right? So basically, that is 2 matrix multiplications. One matrix multiplication between Q and KT, okay? The other matrix multiplication between that result and the value. And then in the middle, there's a softmax layer in the middle. So we can also have this QKB in multiple heads to capture different information, different representation. Right? So each head is basically we have a separate projection matrices for the Q, K, and V for different heads. Okay, we pass through the Q, K, V with these transformation matrices, which is basically just a linear layer. Right? So after this linear layer, which is corresponding to these red parts, okay, and we put it into this scaled dot product attention, okay, which is on the right hand side, and also finally we pass it through another linear. Okay? So basically, there's matrix multiplication, another two matrix multiplication, and another matrix multiplication. Okay. So this is basically the architecture of multi-head attention. Finally, we can concatenate the output values, okay, so that we can feed it to the FFN layer. The interesting part here is that although we have separate matrices for the projection of QKV, since GPU is good at batch processing, right? So it's better to do them at the same time. So actually, we can do the transformation for different heads using a combined projection matrix rather than doing multiple small projections. We can just do one big projection. Okay. All right, and then for the FFN layer, it's pretty simple. So that is the output of the multi-head self-attention, and we pass it through to FFN to fully connected layers. But the different thing here is that pay attention to the dimension, right? So nowadays, these large language models are growing pretty big, like 175 billion parameters. And even one GPU cannot hold it. Right? So the dimension of the FFN layer can be as large as 12,000, right? So 12,000 matrix multiplied by something like 3,000 dimension, right? That could be a pretty big dimension. Sometimes even one single GPU is pretty slow. You have to parallelize such matrix multiplication across multiple GPUs. Right? Although it's a simple, just FFN layer, but from the engineering perspective, there's a lot of engineering that is behind the rack, right? Since the dimension is so big, in order to have a bigger capacity to understand the complicated relationships in our language. All right, another concept is this position embedding, right? So the position matters. For example, a word, they have certain distance, right? No matter if it's in the first part of the sentence or it's in the later part of the sentence, as long as the relative distance is the same, they probably share some similar properties, right? So the positional embedding is providing such information. What is the number, the ID in a sequence? Is it in the early part, the middle part, or the later part? Okay. So a good position embedding should have the certain properties. Okay, it should be unique. So each word's position, you have to have a unique encoding. And the distance between any two positions should be consistent across, no matter if it's a long sentence or if it is a short sentence. Okay, the distance between any two positions should be the same. And deterministic, okay, cannot be random, and that also should generalize to short or long sentences, right? So in order to use this feature, okay, the distance, if the distance is the same, no matter if the total distance is how long is that, we have to have the same relationship. So that makes us naturally think about this sine and cosine functions, since it is periodical, right? So we have this visualization of the position encoding. Okay, so here is the t dimension, and here is the I dimension, right? So here is the t dimension indicating this is the start of the sentence, and this is the end of the sentence. Okay, and this is the dimension of the encoding. Right? So we can see this very clear periodic pattern, which is coming from the sine and cosine function. And secondly, we can find initially when I is pretty small, like in the first couple of dimensions, okay, when I is pretty small, k is also small, right? So the denominator is small, meaning that omega is pretty large, showing that the frequency is actually pretty large because omega is large, k is small. Right? So in the beginning couple of dimensions, the frequency of change is pretty rapid, right? Along different t, okay? So the value is changing pretty rapidly. But as we go deeper into the hidden dimension, when I is getting larger, okay, in this example, we have like 150 dimensions for each position. And here we have 50 positions, and each position we have 150 dimensions, right? So when we get into like 100 pretty big dimension, the I becomes larger, so K becomes larger. K becomes larger, so omega becomes smaller, right? So the frequency is getting smaller. Therefore, in this dimension, it's not changing much. We get to this higher dimension, right? Well, here the frequency is changing pretty rapidly, right? High frequency, low frequency. Okay. So, any questions on the positional embedding?
Due to the periodic nature of sine and cosine, if your sequence is long enough, won't you eventually start getting repeats? Like if your t is much larger than omega, won't you start seeing, like, is it actually unique or is it unique up to just the number of t's that can fit?
You have two different dimensions, right? You have also multiple I dimension for a given t. You don't only have just one single dimension, but you have you have multiple dimensions across the I, across the row wise. That's why you not just have a single embedding encoding, but you have multiple such encodings, okay, corresponding to I. Different frequencies, and they are increasing linearly, right? Higher and higher. When I is increasing, K is increasing, and omega is decreasing. So that's why you have so many frequencies. All right, and let's see what is the correlation between different positions. Actually, we can see a very clear diagonal pattern, meaning that the adjacent positions, their features, their encodings, embeddings are also highly correlated compared with farther distance. Okay. All right, so let's shift gear to talk about the other components in the transformer, okay, which is the layer normalization. Okay, so previously we talked about this batch normalization in CNNs, which can be folded into the weights. Right? So this is feature dimension, this is batch dimension. Okay, this is this sentence length dimension. But here we are doing normalization in a different dimension. Okay, so this is different tokens, different words. This is different sentences, the batch dimension. Okay, and here you have multiple sentences, multiple words in a sentence. Here you have multiple sentences. Okay, and for each.
Okay, I found this on the web for where is in a set.
My series trigger. So here, did I say? No. So among different tokens, right, we have multiple hidden dimensions. We have multiple dimensions in the feature dimension, right? So when feeding each token into the attention mechanism, we want to make sure they are all centered around zero, has a zero mean, okay, and also a variance of 1, right? So want to normalize each token, right? So there are different tokens, okay. For each token, we want them to be centered at 0, okay, with 0 mean and variance of 1, right? So that is the motivation for the layer norm, right? So there's some bad thing and good thing about this layer norm. The bad thing is that the layer norm cannot be folded into the batch normalization, right? So batch normalization is more efficient for inference, right? So there are several efforts trying to use batch normalization instead of the layer normalization, like these two pieces of work. All right, so let's see some results of transformer versus these conventional models. Okay, so given this neural machine translation task, this transformer can achieve higher blue score, which is a metric measuring the quality of the translation. Well, you can see the training cost measured in flops is 1 or 2 or even 3 orders of magnitude smaller compared with these non-transformer models. right? So that makes transformers very attractive for these NLP tasks, offering higher quality at a lower cost. Okay, so remember we previously talked about this word embedding, right? And we have to make each word have a vector to represent each word. But how are those embeddings learned? Okay, and those embeddings are actually learned by language models. Okay, so there are two ways, very popular ways to build a language model. One is the causal language model. The other is the mask language model, like BERT, which you could commonly heard of, right? So for this, for the first one here, we want to try to predict, given a sequence of words, we want to predict the last word, right? Given on the previous word, we want to predict the last word on a pre-trained data set, and then we fine-tune the model with a much smaller data set. Like the GPT model is using that way. And mass language model is also pretty popular, like the BERT model. Okay, so we want to mask away certain words, and we want to predict what is over there. Like here, we try to predict this word boring. So here we first insert a mask, okay, which is a special token. Okay, we feed this sentence. Okay, this is six tokens. Okay, so finally, after this transformer, we are going to get a 6 times the hidden dimension, 6 times d vector, and we are going to pick out that particular position, okay, and to try to classify what it is. And we try to use the ground truth to supervise this training process, okay, so that we can get the embedding for all these words. Okay? So this is basically masked language model. Okay, we mask maybe 15%, some percentage of the input tokens at random, and try to predict those masked tokens, right? So that is actually also echoes really well with those traditional language models that is using the neighboring words to predict the center word, or using the center word to predict the neighboring words. Another self-supervised task we can use to build the language model is the next sentence prediction. Right? Because finally, do a better prediction whether it's the next sentence or not. Okay? Choose two sentences, A and B, and predict whether it is actual next sentence or is totally irrelevant, is a random sentence. Okay, so let's see some applications beyond natural language. For example, we can also apply these transformers to vision models. Okay, so in this paper, an image is actually worth 16 by 16 words, right? Which is pretty interesting that we can further divide the input image into several tokens. Right? For example, this image has been divided into 9 tokens, and then we can run this feature extraction inside each token. Well, among different tokens, we just first do some projection to flatten of the flattened patches, and then we can feed these tokens to the transformer. Okay, this is like 9 different tokens, as if you have a sentence of 9 words, right? We are going to append one over another, just like if you have a natural language. Okay? So we can call this image patches into token. Right? So for the transformer, again, we have this multi-head self-attention followed by this FFN layer. Okay? And we also have this layer normalization and also the bypass together with those position encodings. Right? So using this method, we can also understand images and also the videos. Okay, like video transformer, VIVIT, right? So video transformer, you can imagine is pretty expensive since we not only have to capture the spatial information, but also the temporal information, right? If we do attention across these 2 spaces, that is pretty big, a lot of computation. So one approach is to do them separately, to the spatial attention and then temporal, or factorize the self-attention, spatial first and then last, spatial and temporal. or we can do factorizing dot product at different levels, try to decouple spatial and temporal and reduce the cost. There is also this thing called audio transformer, right? Since audio, if you get a spectrogram of audio, it looks very similar to the image. Right? The frequency, the strength of different frequencies, we have this spectrogram. Therefore, we can further chop it into different patches. Okay? For each patch, we run the linear projection on each patch so that they become tokens. And once they become tokens, we can feed it into the transformer encoder and pass it through the vision layer and also get the output with a special token on the front. So this shares very similar technique as the vision transformer, just use the spectrogram as the input representation of the audio. And then we also have this multimodal transformer. Multimodal means we can feed both the video, the audio waveform, and also the text that is corresponding to the audio waveform. Right? And here we can try to learn the relationship. Right? For example, the same video and the waveform corresponding to that video, they should have a closer relationship than the video and the other waveforms that is not belonging to the same video. Right? So we can also try to make sure that the text corresponding to the video versus the same video's waveform, they should have a closer relationship. Right? So in that way, we can actually use this multimodal projection pad for video feature, the audio feature, and also the text feature to process them together. So therefore, recently we have seen that these transformer models are getting super big, getting pretty large capacity for different modalities, for audio, for video, for natural language, for even for images, a lot of different modalities together. And so also the model size are getting pretty big, 170 billion parameters, which is motivating us to build efficient techniques, right, to make those transformers lightweighted. So there are a lot of approaches that try to reduce the computation and make transformers more efficient. So in this survey paper, they can roughly be categorized into several methods. Many of them we have learned before, for example, by utilizing sparsity, and factorization, low rank, here memory downsampling, recurrence, learnable patterns. Right? So we are going to jump into several of them. They can roughly be categorized into two categories. Right? Some of them are very general techniques that can also work for CNNs, for MLPs, for other vision models. Some of them are specific to transformers. Right? For example, we first learned these techniques that are specific to transformers. For example, this blockwise attention. So previously, imagine you have a pretty long sentence, each word attend to each other. Right? So that is very computationally also memory expensive, because the attention map, the memory consumption is proportional to the n square. N is the number of tokens. So imagine if you have pretty large n square can also be really big. But can we divide the whole sentence into maybe two parts? Okay? And the first part only pay attention to itself. The second part is only pay attention to itself. Right? So that is this pattern. Right? We can divide it into groups, or we can do it in this way. The first part only pay attention to the second part only pay attention to the first part. So we can further do more complicated patterns to encourage those local attention. Right? So this is the masking matrix. So we can drastically reduce the computation by sparsely masking the matrix. Okay. We can also choose multiple patterns at the same time by using different heads. Okay? Head 1, head 2, head 3 for different patterns to increase the capacity. Since remember, we have this multi-head attention, and each head can actually correspond to different masking matrices. Okay? So in this way, how much computation is reduced? So previously, the complexity of the attention map is n by n tokens. Okay, they each token attend to each other. Right? So now, if we have a block size of b, okay, the complexity is reduced to n times b. Okay, where n is block size, either divided by 2 in this case, or divided by 3 in that case. Okay. The paper shows we can reduce the memory to about 18 to 36%. The training time is less than a quarter. Okay. And the inference time is also a quarter less, okay, which is pretty exciting.
Does that really work for all cases? Like in some languages, you'll have a verb that starts at the beginning and then picks up with like a very necessary part of it at the very end. I can imagine that would be a disaster with that, right? If the first part can't attend to the second part.
Right, exactly. If the first part only attend to the first part, that is problematic. That's why we try to increase the diversity by having a more fine-grained and more diverse pattern. And imagine if in one layer you have 1 attend to 3, a second layer 3 attend to 2, so that corresponds to 1 also attend to 2 after 2 layers. Layer 1, 1 attend to 3. Layer 2, 3 attend to 2. So altogether, it's as if 1 is attending to 2. But of course, it's not as obvious and straightforward as you have everything in one layer. So exactly to solve the thing that you mentioned, we try to balance and have a larger receptive field. Right? So people compared with this full n square attention, where each word attend to each word, you have the entire n square each entire attention map. People have this window attention, since usually adjacent words, they are more important to each other. And further away, if the distance is further, the relationship might be weaker. But that suffers from the problem where sometimes the first word has strong relationship with the very last word. So how do we deal with those issues? People try to use this dilated sliding window, right, to expand the region that one word can attend to not only its adjacent neighbors, but something, some tokens that is even further away, right? By using this dilated sliding window, okay, analogous to this dilated CNNs. And also people can combine this global plus this sliding window. For example, a certain word, they are super critical, super important. They have to attend to all the other words for the entire row or the entire column. Right? So we have a couple of such allow such kind of global plus sliding window. Right? This sliding window, those are the global tokens. Right? This token have to attend to all the other tokens. And also for this one, it is attending the first two, they are going to attend to all the other tokens. Right? And very interestingly, this Big Bird paper also proposed to run this random attention. Right? So naively, we may think random attention doesn't make sense at all. But if you think it deeper, right, you have a couple of such random attention, right? For example, token 1 can attend to token 2 in layer 1, layer 3, token 2 may be attending to layer 11 in layer, and then in layer 3, token 11 is attending to token 75. So after 3 layers, token 1 can attend to token 75. If you have a lot of such random attentions, quickly all the tokens can attend to each other. Right? So information can actually flow fast between any pair of nodes. Right? Rapid mixing time using this random walks. Okay, so in this paper, it's proposing combining 3 parts. Okay? One is the random attention, okay, pretty random, and then this window attention only on the adjacent tokens, closer tokens, and this global attentions. Right, this word has to attend to all the other tokens. Very important word for example. The Big Bird is combining these 3 all together. Okay, all the white colors they don't have to compute. They save the computation. They only have to compute can store those those tokens with the color. Okay? Those locations with the color. So that's the idea for Big Bird. Random attention plus local attention plus global attention. Right. Since this window attention reminded us of something, right? Convolution is very good at this kind of window attention, since it is only not modeling the relationship between the close neighbors, right? So why not just using convolution to model such window attention, right? So in 2020, actually, we published this paper called the light transformer that exactly implement this idea, right? So we can see the attention map of a sentence usually have this diagonal pattern, right? Showing that we can the words closer to each other is very important. So why not just use convolution to model such window attention and use transformer to only model this global information, right? So using that, we propose this long, short range attention and using convolution to efficiently extract those local features and attention to specialize that for extracting the global features. Okay? So this is the global feature extractor, the attention mechanism. This is the local feature extractor by using convolution. Right? And for each layer, we have these two branches. Okay? They are going to be concatenated together in the end. So to deal with a lot of tokens, in particular for images, right? Image is unlike natural language, where natural language is just 1D, but image is 2D, right? So if you have an image size of h by w, the total feature map size is hw square, right? Which can be pretty big, right? So hw, since there's n complexity for the multi image, right? O(n) square complexity, right? And n here is equal to h times w. So altogether is hw square. Right? So people propose another technique to do the attention mechanism separately, okay, for the weights and for the rows and for the columns, right? Rather than each pixel attend to each other, each pixel only attend to the neighbors in the same column or the other pixels in the same row, right? So we can do them separately so that the total complexity is no longer hw square, but h square plus w square. Okay? So the idea is to factorize the attention along different axes. In particular for image, that works since image is 2D. For video, that works, video is 3D. Okay? To reduce the complexity from hw square to h square plus w square. All right, so next one, we also have this kind of sparse attention in reformer, right? So again, remember this attention matrix. We can have this bucketed solution where the first bucket only attends to itself, second bucket only attends to the tokens in the second bucket. Okay? So how do we enforce such bucketing? Right? So here we're using a technique called locality sensitive hashing technique to get the hash for each token, and then we group the similar tokens together, right? Blue tokens, yellow and red tokens together, okay? And we group them into same batch size, so it is easy to process, okay? So that we are only paying attention to the neighboring colors, same color altogether, but this blue and this yellow are not pay attention to each other. Okay, so the key idea is to group similar vectors into the same bucket, since if they are from the different buckets, they are not related to each other, not similar to each other. Okay, so it's a waste of computation to compute, for example, between the blue token and the red token. Okay, so using that intuition, we are using this locality sensitive hashing to group the tokens and only do attention within the group. So as we mentioned, transformers are getting super big. Previously, we are playing with these models like a couple of 100 million parameters, but now we are dealing with something that's hundreds of billions of parameters, or even trillions of parameters, which is getting super big in recent years. So quantizing these weights and activations can actually save the memory and also communication overhead. So for today's lecture, we'll first discuss about those quantization techniques. So especially those post-training techniques for efficient inference with large language models. Why are we targeting post-training? Because training these super big models are super expensive, right? Require a lot of resources to train this model, right? So for efficient deployment, can we have a training-free method that we can quantize those models, both weights and activations, to 8 bits to save the memory computation? But this is not easy, right? So we can see this is as the model grows, okay, from 1 billion to 175 billion. The accuracy using the naive 8-bit weight, 8-bit activation quantization, which we introduced in previous lectures, the accuracy begins to drop with a model size larger than 6.7 billion parameters, right? So which is a very drastic degradation of accuracy, right? So actually we find there are a lot of outliers, super big values in those activation values that is destroying the accuracy. A previous work tried to preserve this accuracy by introducing this IP16 to represent those super big outliers, right? That can preserve the accuracy. However, you have a mixed precision of IP16 versus int8, right? Making the inference actually slower than purely IP16 implementation, right? So it's super crucial to have measured latency saving and also the measured memory saving for such quantizing of large language models. So today's lecture, we are going to introduce this SmoothQuant technique, okay, which is accurate and efficient post-training technique for large language models, okay, from Guangxue and Ji's recent research just posted. So we summarize a few characteristics. What ideally, what is the case that we want, right? So we hope to fully preserve the accuracy for large language models over 100 billion parameters, right? And at the same time, we want it to be efficient to implement them and achieve measured speed up and memory saving using workloads on the hardware, right? So actually, SmoothQuant can achieve the best of both worlds. And the key idea here is that we find the activations are very difficult to quantize, right? There's some outliers that are super big across certain channels, which is the same for all the tokens, right? So for the remaining values, the effective number of effective bits is actually pretty low. Relative to that, the weights are actually much easier to quantize. The distribution is much more friendly compared with the activation, which has a lot of big outliers. Since activation is difficult to quantize, we just redistribute the quantization difficulty. For example, we smooth the weights that was before so that we can make weights easier to activations easier to quantize, right? And we push some of the quantization difficulty from activations to the weights, right? So that we can have a easier to quantize activations, slightly more difficult to quantize for the weight, but it's still relatively easy and okay to quantize using the techniques that we already have. So originally, activations are hard to quantize, weights are super easy to quantize. Now both of them are relatively easy to quantize. Okay? So push the quantization difficulty from activation to weight. Right? Just like if you find something difficult, just give the difficulty to someone else. So, but it turned out to be both weights and activations after that can be quantized to 8 bits without any loss of accuracy. So let's see in depth how that works in a real large language model. For example, the original activation we find across different tokens, several channels had super large values across different tokens, right? No matter which token it is, this last channel has very big values. Similar for this channel, okay, super big values. Okay. But the weight previous before the quantization is actually pretty flat and relatively easy to quantize. Imagine we have 256 values. You want to divide this whole range. The actual effective number of bits for these blue activations are actually only very few bits are useful, right? So those outliers is really killing us from being able to quantize those activations very effectively, right? So what do? Right? We do smoothing, right? We try to smooth the weight to make it to be something like this, right? For example, this channel is super big, then I multiply some small number so that it can be something smaller, right? To make sure it's mathematically equal, I just want to multiply with something bigger so that the weight becomes bigger, so that the multiplication result, the product between the activation and weight, they keep the same, right? So we can see for certain channels that used to be pretty big, after smoothing, they become much smaller. And on the contrary, the weight becomes bigger in those channels that has big activation. And so this is basically migrating the quantization difficulty from the activation to the weight, right? So we are also smoothing the activation so that there are less outliers. This is mathematically equal because the weight multiplied by the activation, they scale in the same in a different direction. One is getting smaller, one is getting bigger. You multiply them together, the product is the same as if nothing has ever happened. So using this method, we can perform this kind of tensor quantization in one single step size for both the activation and also the weight, right? So here, we're comparing different tensor per token versus per channel quantization accuracy. And you can imagine from this per tensor to per token versus per channel, which accuracy might be easier to maintain. So here we have a single scaling factor, a single step size for the entire tensor. That's why we call it per tensor quantization. Well, for per token, we have one step size, one scaling factor for one row. Okay, and one per channel, we have one scaling factor per column. So which one of these might be easier to maintain the accuracy? The second one. Why is not the first one?
I thought each tensor has multiple channels and tokens.
Right, you have more flexibility in this case, right? Rather than having a single step size for the entire tensor, you can have finer granularity of the of control, right? But which one is easier to accelerate on hardware? First one, right? So you have only one single multiplier for the whole tensor. So that's the two sides of the world. One is easier to accelerate, but harder to get a good accuracy. And actually, that's exactly the case. You get a very large drop of accuracy using this top per tensor quantization, right? Although it's easier to implement, easier to accelerate, but using the per channel quantization, you have a lot of flexibility. You can have one scaling factor for each channel, but it's difficult to implement in hardware. Right? You have so fine-grained control, and you have to scale. Actually, that's not very difficult to accelerate using the existing gem kernels because the per channel per per channel quantization, especially if you deal with the inner dimension, is actually impossible to directly use those giant kernels. But only outside channel, output channel, you can do some tricks to achieve that, right? So how do we get the best of both worlds to get a fast and also high accuracy implementation? So this is how SmoothQuant does, right? So this is activation matrix. This is original weight matrix. Okay? So each row will be multiplied with each column and produce one result, right? We can see some of the activations are really big in their absolute value, right? So this minus 16 will be multiplied with positive 1, right? So can we rearrange this weight and activation such that we are multiplying minus 4 with plus 4? Okay, you see, they are both getting minus 16. Okay? Minus 16. It's also minus 16. But after this smoothing, okay, the difference between the max value and smallest value, they are much closer, right? So this is how we do this smoothing and pushing the quantization difficulty from the activation, which is having something that's very difficult to quantize, and push them to the weight. So how do we do that? We find the max of the absolute value. Okay, in this column is the max of the absolute value is 2. Okay, for this column is 16. For this column is 1, and this is 9. And here we find a max of the absolute value across the row dimension for the weight. Right. So this column, this row is 2. This row is 1, 4, 1, etc. Right. So we have these two vectors, which we just divide the max of the x, which is this vector. Okay. And I have an element y, divide that by the max of w absolute value. Okay. So what we get is actually this vector. Okay, 1, 4, 2, 3. This is 1, and this is 16 divided by 1. And have a square root of that, so we get 4. And then 1, 4 square root, get 2, etc. The last one, 9 divided by 1, the square root, that is 3. So we have this scaling factor, and we call it the smoothing strength. Right? So we can smooth the equation by dividing this original x by this smoothing factor. Right? So 1 divided by 1 is 1, but this minus 16 divided by 4, that's minus 4. On the other side, for the weight, rather than dividing the s, we want to multiply w by s. For example, this is the original w. Okay? This is the s, the scaling factor. Okay, and for each row, the first row will be multiplied with 1. Second row will be multiplied with 4, etc. Right. So multiplying the activation, the weight becomes exactly the same as before. Since we're dividing as here and multiplying as here. So putting them together, they actually cancel each other. So the resulting result is exactly the same.
But are you doing smoothing in floating point domain?
Now the question is, are you doing the smoothing the floating point domain? So let me see. You do the smoothing first, and then you quantize.
Yeah, which like increases computation in the.
Actually, not, because this is done before the inference. You can do this at compile time. You can do it only once.
Activation has different max value, right?
So the way we do it is here. Activation has different value, but we use a calibration data set that is maybe have a subset of the sentences in the training data set, and you use those to calculate the max of the ABS max to collect those statistics offline, and then use that offline collected statistics as the calibration to define this vector. Yeah, so everything here is purely static. It's done at compile time in the original floating point manner, so that we can quantize them before doing any inference. Very good question. All right, so let's see at runtime what happens. Right? So this is QKV, like we mentioned in the last lecture, how the attention mechanism works. Right, we have two BMM batch matrix multiplication. One is calculating the attention map. The other is the weighted sum of the attention map versus the V vector. And all the green parts, now we can process them in int8, right? Those are the weight lifting parts, like the QKV transformation, the BMM, and projection, and finally the two FC layers. Okay, they are all done by int8. And those linear layers, like layer norm, softmax, element wise, add, etc., they can be processed by P16, which has very low overhead. Right? So we also tried 3 different strategies. Okay? So for the weights, we also always do the per tensor quantization for all these scenarios, since weight is relatively easy to quantize. And for activation, we do O1, O2, O3, which represent the per token dynamic, like what you mentioned, we do it at runtime, versus static, we collect those scaling factor using calibration data set before the runtime. Static. And per tensor, static is the strongest optimization where it's fastest, you can imagine. Because everything is done static by compile time, and it's per tensor quantization, very easy to implement, but you can imagine this may have a lower accuracy. But let's see, how did we recover the accuracy using this setting? So for O1, O2, O3, this is the Lambda data set, which is very popular these days. The baseline is the P16 accuracy. We are getting roughly, this is 64.7% accuracy. Naively using 8-bit integer, very unfortunate 0% accuracy. For this OPT 175 billion model, right? The model is so big, there's a lot of outliers, like as you can see in the previous figure, right? So lots of outliers, very difficult to quantize. If you quantize 8-bit, this might occupy the whole dynamic. Everything else will be dwarfed. You cannot, they are not visible, so that the naive quantization doesn't work. Other methods like SmoothQuant also doesn't work. We even tried, for example, not quantizing some of the QKV projection layers, but again, that doesn't rescue this this method. In 8 introduces this mixed precision. So for those outliers, those big skyscrapers, they use P16 to quantize them. So they have a mixture of int8 and P16. That can indeed have a pretty good accuracy, but it's very difficult to implement. And the measure to speed up is actually less than 1, means it's actually slowing down the inference. And outlier suppression cannot solve the issue either. But using SmoothQuant, to push the quantization difficulty from weight activation to weight, using O1, O2, we can actually pretty much fully recover the accuracy. Even using O3, the static per tensor, the most hardware-friendly quantization method, only 0.1% loss of accuracy, meaning that we can very accurately, with minimum drop of accuracy, while fully quantizing both the weight and activation for efficient inference. This is overall accuracy amongst all different downstream tasks versus weekly tasks, which is the lower the better. So that's why we didn't average the last column. So overall, the average accuracy is well maintained, even using this per tensor static weight and activation quantization. Okay, so we also tried some of the world's largest open source large language models with 175 billion parameters, Bloom with 176 billion parameters. Okay, imagine you have a GPU that has 40 gigabytes of memory. Think how many GPUs you need to support this? That is 5. Right? It's a super big model even for inference, you need multiple GPUs, and the GLM 130 billion parameters, which is also have a lot of outliers, difficult to quantize, but using SmoothQuant, we can recover the accuracy pretty well using the 8-bit weight, 8-bit integer, 8-bit activation. If you quantize from 8-bit to 16 to 8, that will mean you can use fewer GPUs. Yeah, exactly. Right, possibly a factor of 2. For example, here we are showing these speed up numbers. Okay, so this is across different batch size and different number of tokens. So across different model sizes, right? So here we have different size of the model. This is 16 billion parameter, 30 billion, 66 billion, 175 billion. For example, if you look at this, previously we used 8 GPUs for this gray line. Now we need only 4 GPUs in this red line, but latency is actually even shorter. With 8 GPUs previously without quantization require 848 milliseconds. Now we have half the number of GPUs, while the latency is only 720 milliseconds, even faster, and we reduce the number of GPUs by half. So that's a pretty cool technique to reduce the serving cost. Okay, so go back to our presentation here. Across, we can verify the method works pretty well across the available models we can verify, but of course there are a lot of large language models coming up, open source and open source. Very welcome to check out for other repos. So this is an interesting study about the migration structure, right? So we are migrating the quantization difficulty from activation to wait, right? So there must be a sweet spot, right? If we migrate too much difficulty all the way to the activation, what happens? So the accuracy becomes very easy to quantize, but the weight becomes super difficult to quantize. So the overall accuracy is very low. Right? If alpha is small, which means we just offload a little bit of quantization difficulty from activation to wait. And what happens for that? Still pretty poor accuracy because we are not adjusting enough strength to alleviate the quantization difficulty on the activations. Right? So in the middle, around 0.5, that's the sweet spot. Right? That's why we have the square root, right? Square root, which is alpha of 0.5, so that we have a more balanced migration of the quantization difficulty from activation to wait. All right, so this is the PyTorch implementation for different size of the models. So we implement all the way up to 30 billion parameter models so that we can deal with a 6000 GPU. Here we can measure the speed across 3 different frameworks. Original baseline, okay, in A versus our method. So for the LM in A across multiple scenarios, like here, it's actually slowing down the inference due to the mixed precision with both P16 and int8. Right? So by pushing everything to int8, it's possible to get pretty good speed up, and also using half the GPU memory compared with the P16 counterpart. And this is using a single 180 gigabytes of GPU. And then we collaborated with NVIDIA to try it with even bigger models, okay, using more number of GPUs. For example, 66 billion parameter model, 175 billion parameter model. The speed up is pretty awesome. Like for this case, previously using 2 GPUs to achieve 489 milliseconds. Now we can achieve that using only a single GPU, okay, reducing the number of GPUs by half. All right, so that's the technique we covered about quantization, right? We also described a lot of other techniques in the first part of this lecture, and let's see how do we apply that to large language models. For example, neural architecture search, rather than manual architecture search to tune different hyperparameters, right? Can we use this machine learning, use different algorithms to automatically find the best fit neural architecture for a particular hardware architecture? But keep in mind, this NAS sometimes require this training, fine tuning, right? But this large language model is pretty big. The training time is very long, so we have to pay extreme attention for such algorithms. So far, let's talk about these middle or small size language models, which is affordable for us to do this neural architecture search. This is an earlier work of Google called Evolve Transformer. That is an early exploration about trying to find the best architecture for these transformer paths. Right? So it is NAS style blocks. Okay? We have two hidden states, and the output is a new hidden state. The search space includes the decoder and also the encoder, okay, which has 6 and 8 blocks each. They use evolutionary architecture search, similar to what we did in the homework, and actually compared with the transformer baseline, they compare the means of pattern versus the machine translation blue for actually evolved transformer and outperform this human designed base transformer model. But pay attention here, the median parameter is actually not quite big, about 200 million parameters compared with what we just described about quantization. We are actually dealing with 175 billion parameter model. So there's still a big gap if we can do neural architecture search on such big transformers, since training, even training only once becomes super expensive. To reduce the training cost, we actually Henry did awesome work on hardware-aware transformer (HAT), and applying neural architecture search, actually using the once-for-all technique like we did in the homework to perform this hardware-aware transformer architecture search. An observation is that the flops versus the latency is not growing in the same rate across different dimensions. For example, scaling the hidden dimension, okay, which is orange line, versus scaling this embedding dimension versus the number of layers. Okay? So the number of layers, it is the most sensitive with the latency. Well, CPU and GPU, especially the GPU, scaling the hidden dimension or the embedding dimension almost has no effect on the latency, right? Since the NVIDIA GPU has such a large parameter, right? If you are not feeding it with enough workload, it's going to get hungry. Right? So scaling the hidden dimension and embedding dimension doesn't help with reducing latency. And turn out scaling the layer actually can shrink or grow the latency very effectively, right? So which motivates us to do such hardware-aware architecture search, because for certain hardware, changing certain dimensions has no impact, but for other hardware platforms, it might be very effective, right? But can we build one model and then specialize the different subnetworks for different hardware platforms? Okay, so that's exactly the once-for-all idea we described. So we make it possible to have elastic dimensions across the encoder layer. We have the elastic number of layers in the encoder, the elastic hidden dimensions in the FFM, elastic number of heads. It can be 1 head, 2 head, 4 heads, etc. And also elastic embedding dimension. Right? So different from the conventional transformer, now different dimensions can grow or shrink. Okay. And then we have a evolutionary search engine, okay, giving the latency feedback. Always propose a new sub-transformer architecture, which feeds into a latency predictor, okay, to get the latency of the CPU, GPU, IoT, whatever hardware you are using on the bottom, using this latency feedback in the evolutionary search engine, just like what we did in the homework for vision tasks. So again, using a super transformer, a once-for-all transformer, we can get different sub-transformers and deploy a smaller one for the IoT, larger one for the GPU. And here we are fully aware of the characteristic of the underlying hardware so that we can design customized and specialized transformer for different hardware platforms. Such as for Raspberry Pi, we can get about 3x faster inference, and you have CPU about 2x faster inference. Then you get Raspberry Pi, and you get GPU, etc. So we can design the best fit pairs of the transformer architecture versus different hardware platforms. And once for all, really propose a mechanism to enable such hardware-aware transformer where you train only once, and then you can obtain different subnetworks and reuse it many, many times during the search. All right, in the lecture 10, we also learned about knowledge distillation. Now it's a good time to revisit that in the context of large language model, right? Just a quick recap: what is knowledge distillation? Teacher network, that was smaller student network. We both generate some logics. We want to have a distillation loss, try to match the logics between the teacher model and the student model, apart from its original classification loss. And there could be multiple places where we can inject such distillation loss, both in the end of the network and also in the middle of the intermediate layers. So for transformers, where are the opportunities where we can inject the distillation loss? So let's look at this slide, which is the famous distill birds, right? So we can distill the attention, of course, right? The student learns to fit the matrix of the multi-hat attention as the teacher network, try to match their attention matrix between the teacher and the student. Number of hats, token size times the token size. Okay. What else can we try to match? Hidden states. Right? And distill the knowledge from the output of the transformer block. Although the student may have a smaller dimension, therefore we need a linear projection to match the dimension before we insert the distillation loss. We can also distill the embedding, okay, very similar to the hidden state. And finally, we can insert distillation loss in the final prediction. So we can insert either in the hidden state or in the embedding or the final prediction across these 4 dimensions. All right, so apart from these algorithm innovations, we also want to introduce some piece of work, which is providing the system support to accelerate these big transformers. A very famous one is flash attention from Stanford. And remember, we talked about this memory hierarchy in our previous lecture, that we have this pyramid of memory hierarchy where the SRAM is very fast, but pretty small. The main memory is slower but bigger, right? So we want to keep as much as possible in the SRAM rather than having go to the DRAM, which causes more off-chip data movement, which is expensive. Right? So rather than calculating the entire attention map and materialize them, store them into the DRAM, okay, we want to compute them on the fly, block them and do as much as contents in the SRAM on the fly, rather than having to materialize the intermediate results, for example, the entire attention map into the DRAM. So that by such fusion, we can reduce a large proportion of the calculations before masking, softmax, dropout, and more the fuse kernel is taking a lot smaller latency compared with the baseline. And the rule of thumb is to reduce data movement, reduce number of read and writes, and try to fuse as much kernels as possible. And this is the flash attention speed up about 2x or even more across different sequence lengths. And there are other very popular works if you want to work with this large language model acceleration, including this famous faster transformer from NVIDIA, which we already integrated our SmoothQuant, which is actually going to be released later this month, and also Deep Speed from Microsoft, together with very full-fledged infrastructure across different workloads, and also this Fossil AI, even for different workloads, and this Alpha from Berkeley, dealing with this automatic parallelization across different dimensions, which we talk about that in the distributed training lecture. And auto parallel, having this hierarchical parallel, you can do model parallelism, you can do data parallelism. For model parallelism, you can do it at different granularities at the tensor level, pipeline parallelism, everything. Highly recommend to check out these techniques. So in summary, in today's lecture, we finished to talk about these efficient techniques for transformers. In particular, talk about this quantization approach using SmoothQuant to smooth those outliers and migrate the quantization difficulty from the activation to the weight and enable per tensor static quantization for both the weight and activation to achieve measured speed up and measured memory saving. Right? And we also talk about a lot of system support and other techniques to make these large language models and transformers run faster. All right, so that's the first part of this lecture, and also the conclusion part for the entire classic efficient deep learning content. Right? In retrospect, we learned both about inference and about training. Right? In inference, we talk about pruning, quantization, knowledge distillation, neural architecture search. We also revisited them very recently. And also in training, we talk about on-device training, fine-tune the last layer, fine-tune the bias only, sparse update, quantization, where scaling. Right? And we also talk about distributed training across multiple machines, multiple nodes, how to do parallelism, how to reduce the latency and bandwidth using gradient compression and delayed update to tolerate the latency, right? Finally, we talk about these application-specific optimizations, especially for those computationally intensive workloads beyond 2D vision, right? For example, 3D vision, adding the Z dimension, and also the videos, adding the T dimension, and also the GAN models, right? And also the transformers in natural language, right?